evening, dear faculty. So thank you for joining the session. So we'll start the session straight away at 7:30 p.m. Meanwhile, anybody of your colleagues have registered for this program but not yet joined, please inform them to join the session. Good evening, dear faculty. A warm welcome to today's session, day 2 of AI-driven embedded product development (FDP), organized by Sense Academia in association with SSIT Solutions Private Limited. Once again, a warm welcome all of you guys. So let me introduce our resource person to you first. So let me welcome Mr. Sai Shankar Rao, our senior firmware developer at Lohia Top, and he has 8 years of experience as embedded firmware engineering and hardware development. These 15 days FTP will be taken by Mr. Sai Shankar Rao. So without any further delay, I would like to hand over the session to Sai Shankar Rao. Thank you so much. One more thing I want to tell you guys, this is an interactive kind of session. So please post your doubts in chat box. Every doubt will be addressed by our resource person. Thank you. Sai Shankar Bro, please carry on.
Hi, good evening, faculties. We will wait for 2 more minutes to give time to join for the other faculties too. If there are any colleagues or any friends of you are also waiting, please tell them also to join. Within by 7:35 we will be start the session today. Sudhir or Surya?
Yeah. Yes, Sai Shankar, please allow.
Good evening, sir.
Yeah, good.
This is from Baba Institute of Technology and Sciences, Visakhapatnam.
Just want to check that what happened with respect to the VLSI. Is that session complete? I think so. Few of the faculty are joining for both the sessions.
Yes, already VLSI session has been wrapped up. 10 minutes.
Okay.
We'll straight away start the session.
Okay, then we will proceed with this right now.
Yeah.
Hi, good evening, faculties. Once again, this is R. Sai Shankar Rao. Yesterday we had an introduction and brief regarding what we are going to discuss with respect to this FDP and what we are going to give and what are the basic expectations from you. Yeah, all the things has been discussed in detail. As once again, I will give a small brief on this front. If you guys are want to give a small info, like if you guys are having any doubts which is like blocking you, if you are going further ahead when I'm discussing something, you can drop it in the chat box. After the completion of the session, we can discuss in detail, or you can write it in your notes and we can discuss at the end as per our convenience. And even if the time extends, there is no issue, we can extend the time and we can discuss in detail also, no problem with regarding that. Well, coming to the course, here the course has been divided into the 2 major modules, one as the PCB design front as well as the embedded design front. Majorly in the first week of the session, we will be discussing regarding the PCB development and how AI's role is there in the PCB development, friends. As well as later, friends, we will be doing with respect to embedded development. We will be seeing few courses, like few things like GPIO timers and so on. Based on the time permits, we can extend with respect to the protocols and based on the few faculties even asked for the regarding RTOS and Linux too. If time permits, we will touch those topics and at least high level and see in detail too. No problem. As in the initial phase, we will be proceeding with the PCB design. Well, majorly PPT is visible, right? When I am presenting, I cannot see any charts. That is the reason I have said that I cannot see any chart message or something. We can see it in the end. Please respond someone from for the hardware, for the firmware, and for the software. For each of these things, there will be a different kind of teams, and for each of them, there will be different kind of roles as well as different kind of duties they need to be followed in such a way to meet the embedded requirement or a product requirement. We'll be seeing them in detail. While coming to the major hardware team roles, they will be analyze and design an hardware architecture, and after designing an architecture and finalizing an module, before going to doing something, they will test and validate few circuitries and they will go for an implementation on the PCB for a prototype. These are the major roles of a hardware team when they are dealing with a PCB. Coming to the firmware team roles, they will be architects designing with respect to firmware development and how the hardware need to be operated with respect to real-time scenarios. And they will go into the implementation of those firmware. After that, they will make this into the module level testing, and they will test each and every piece of the firmware what they have developed on. And coming to the software team roles, majorly they will be working with UI UX design team, like for the user when they are handling or when they are using, they will be mostly attracted with respect to UI UX design. So the software team will interact, work with UI UX designs and cloud and security managements with respect to IoT when we are dealing with, and data analytics and visualization with respect to, let us say there is a vibration monitor project or some sensing project with respect to a kind of air quality index. To show the same information, we will integrate the sensors and we will collect the sensors with respect to firmware, but where the software team can represent the data very aesthetic way, so the user can understand with efficiently without having hesitate or without getting any wrong information or misinformation from the data. In such a way, the software team roles will be there. Proceed with. And nowadays, we are listening this buzzword called AI, which is nothing but an artificial intelligence in each and every stream and each and every place with respect to the it might be an IT development, it might be an VLSI, it might be an embedded, you name it, in each and every field, AI is placing its own role and it is occupying its own chair when it's coming to an discussion with respect to any technology. So when we are discussing with respect to AI, just to give you a note, like AI is kind of an technology or enhancement which gives lot of information in a single place, which is kind of an other intelligence we can use upon. Okay, and we will be seeing how the AI will have impact in each and every phases of PCB design or an embedded design, and we will be discussing them also in detail. Okay, why AI in embedded PCB design? Basically, what is the major requirement of using an AI? Is like modern products requires increasing complexity electronic designs, as well as product life cycles are getting shorter with rapid market changes. Because of there are huge demand in the market with respect to the boom in the embedded, there is a very critical resources, as well as the number of resource persons are also getting lower, as there are a lot of startup companies which are try to produce a product within an 3.5 months or within a 4 months to meet such kind of time criticality, where this AI is helping in lot of fronts. And coming to high reliability standards are critical for safety and performance, and intense pressure to reduce the development and manufacturing costs need to accelerate the time to market to stay competitive. Nothing but by using an AI in the embedded, which will short out the lot of information, as well which will cut out the time and where we can produce the same product or we can increase the efficiency with respect to timing. And as I said, AI is a junior hardware engineer. Consider, even if you are a fresher or if you are having some knowledge with respect to any development, with respect to any technology, if you use AI as a junior engineer, you can, instead of that AI is replacing you, you can use it as an unpaid assistant for you. So in such a way, you can also develop the same technology or the same work what you are doing or what you are held with in a fast pace, as well as you can 2x your same work with the same speed. Okay, like AI can interrupt and analyze the product requirements very efficiently and suggest the suitable architecture design based on the project constraints, and recommended appropriate components from vast catalogs of parts, because identifying a part is a major headache for any hardware engineer, because there will be a n number of suggestions or n number of options available in the market. To identify or to sort out the data is one of the biggest headache or the biggest challenge for an hardware engineer. So which will help by we can cut out the time by using this AI also. And propose the interface solutions and connectivity options, provides early feasibility analysis and design trade-offs also. By using AI, we can address all of those things, so we can ramp up the speed or the development of a product by using this. And yes, it will be always give suggestions, but there will be a need of engineering validation. Okay, AI models generate probability outputs that need to be verified each and every step. Okay, engineering judgments remains essential for critical decisions. Component datasheet must be manually reviewed by engineer for accuracy. By using AI, you can have a glimpse of datasheet, but to get in full control of any sensor or any module or any component, you need to go through or thoroughly manually. That is how in traditional way still the date it is running in the market. And simulation and testings are required to validate AI suggestions, and compliance with industry standard needs human oversight, because yeah, an AI can think with respect to technology in well-versed way, but it cannot think the real-time site scenario issues, but which it might overseas. But we have to check each and everything in detail, and we have to take the suggestions by using AI, but we should not blindly follow the AI rules. That is what I meant to say, and how we can use the AI with respect to embedded. And coming back to the PCB design, majorly the steps that we will follow in the PCB design is like requirements gathering, analysis and architecture design with module level implementation, circuit designing, proof of concept, and then we will go to the PCB design. We will be discussing regarding each and everything in detail further going ahead, and I will explain. Requirement gathering and analysis. If you consider the each phase wise, the requirements gathering is nothing but what to do. Okay, understanding the end application and its functional needs, defining input, output, requirements and power constraints for the module or for the hardware what we are dealing with, identify key hardware specifications, note mechanical or environment limitations. By keeping all of these, or even there might be other more requirements also based on the project constraints, based on the case to case it might vary, but these kind of things we will be gathering as an requirements to proceed ahead. Okay, well, coming to the analysis, where we are having a base requirements, like for an analogy purpose or for an example purpose, let us say a person want to travel from Delhi to Mumbai. That is a core requirement. So when he want to travel from Delhi to Mumbai, he can go to Delhi to Mumbai via multiple ways, like via bus or via road or via flight. So finding out all possible ways is nothing but an analysis, and identifying the main core requirement is nothing but the requirement gathering. Okay, and in the analysis phase we will explore the various hardware configurations and the topologies, and compare the microcontroller families based on the power, peripheral and cost based on our requirement, and based on that we will trade off and we will come up with a proper controller or proper components what we wanted to select. And evaluate analog versus digital sensor choice and its communication techniques, considering constraints like size, speed, power consumption and expandability too. And review reference designs, application notes and existing implementations if there is any. We will be reviewing them and reference them for ease of development and to make the PCB fail proof. Okay, and coming to the architecture design, the best possible ways with respect to that, design system level block diagram, clearly define major functional blocks like sensing unit, processing unit, output unit, power consumption. All of them will be block level wise, and visualize data and control flow between the components or between the microcontrollers. And we will be also defining the communication protocols, what it need to be happen, like I2C, SPI, UART, CAN, Modbus, or whatever it may be, based on the speed, simplicity, pin availability, and need for the particular project based on the thing. And ensure proper isolation or buffering if required from module to module also. And identify main controller and support components based on its availability and costing in the market at the present time, or based on the project when it is running for, because the costing of a component and the availability of a component will not remain constant more than 10 years. It might be the availability of a component will be varies for every 5 to 6 years generally in the market. So when we are designing a PCB or when we are finalizing a component, we should always think of availability of the module, because with respect to industries at least, when we are designed a circuit and when we have supplied a module, they will expected to give a production run for 15 to 20 years. As a supplier company, they should able to supply the same kind of module or same kind of an hardware without having any issues or without changing in the architecture. But let us say there is a main heart of the component, some controller, which was procured from outside some companies, like some STM controller or NXP controller. Let us say if they are not manufacturing the controller from them itself, then the complete architecture will be ruined. So we have to redesign the same architecture. So these kind of loopholes or these kind of issues might be triggered further going ahead when we are designing a component. So always we have to check for the availability, and the costing of the module also will always be prior with respect to industrial design. Okay, and choose the controls based on the number of IOs, memory, and required peripherals, and decide on supporting components like voltage regulators, drivers, converters, protection circuits, which all are the things required across the microcontroller to work it properly. Okay, and then we will be finalizing the hardware architecture with scalability that keep it in the mind. Like leave a small room for the future upgradation or the expansion of the module if it requires, and modular design for easy debugging, reuse, and updates. As we know, any module or any hardware what we have produced in the industries or which we are using currently in our home also, they we will expect easy to troubleshoot. Let us say there is a washing machine in our home, it went wrong. Usually a service person will come to repair that, but when he is troubleshooting or when he is identifying an issue, he want to debug or he want to troubleshoot the issue. So the module or the design should be easy to debug or even to reuse or to update the same existing module, and define clear interfaces for software and firmware integrations too. And coming to module level implementations, where here we will break down the system into functional modules, as we already discussed, like sensing, controlling, displaying, processing, all of them as individual modules. If there is only a small piece of PCB, we will consider it as a single module and we will be proceeding further. And defining the individual modules and its responsibilities, like from what is the input to this module and what is the output of this module and what is the power resources it need to be used and how thermally it should be performed, and all of these kind of responsibilities we will be writing it on a note in detail and we will be proceeding accordingly. And plan the interfacing between the modules with respect to module, and basic we will be beginning with a basic functional verification for each module, so we can procure out the few modules or we can test it out on the different bins by using preg boards or by using breadboards also. Okay, and if we come to hardware designing, like selecting microcontrollers, power supplies, and interfaces, majorly microcontroller selections like choose based on the processing power. Usually we will be seeing 8-bit, 16-bit, 32-bit ARM Cortex, like how we will see 64-bit Intel core processors. In similar way, these are microcontrollers which are 8-bit, 16-bit, 32-bit, usually available in the market from different makes like STM, NXP, Microchip, and so on, like Infineon and many more companies too. And considering the RAM, flash storage, and GPIO availability based on the architecture requirement. And we will be evaluate the power consumption and different kind of sleep modes, because the use of sleep modes is here nothing but lot of embedded devices right now is working based on the battery based operations. So if it is strongly running on a power base which is like constant power voltage source, so then there is no such kind of need of sleep modes or any such thing. But if some module is running based on the battery based, so we should always think of use the same module by having a less power consumption, so the module can run for a longer duration with the same battery without recharging or without having a huddle out with them. further going ahead. And ensure support for communication protocols like I2C, SPI, UART, CAN, USB, etc. like Ethernet. What the things what are required with respect to the architecture, and factory in cost and availability as we discussed previously. And power supply sections like designing efficient power regulators like linear versus switching regulators. Based on the need, we will be identifying the linear or switching regulator. Ensure battery compatibility and power optimization based on the needs. Okay. And include isolation and protection circuitries like diodes, fuses, transient voltage suppressors is nothing but a TVS diodes. Usually we will call it TVS diodes and so on. And mathematical calculations plays a very vital role with respect to hardware design, like calculation of resistors, capacitor values based on the applications, and in some cases inductors, and lot of interface circuitries which related to the power supply are very critical when we are dealing with the hardware design. And power budget estimation as well as frequency and timing calculations are also vitally important with respect to hardware design. And when we are considering the AI role here with respect to the component selection or the hardware selection, here AI assists in selecting appropriate microcontroller for the application. As I said, it will be having very big headache because of there will be n number of options in the market. So to sort out the data, it will consume more time. So by using an AI assistance, so you can reduce the time and we can have in better options very quickly. And recommends sensor based on the accuracy and interface requirements, and suggest the communication protocols that fit system architecture. Help size voltage regulators based on the power requirements. Identifies alternate components to mitigate the supply chain risks. Here, if you identify the last point, identifies alternate component to mitigate the supply chain risk. Like as in the previous example or the previous analogy, we have seen one small example. Like let us say if we have designed a small PCB or a small module where it is given to an client or to a customer, where he is successfully running the same module without having any issues for a, let us say, for 6 years. After 6 years, some of the component, let us say there is a power supply component, a regulator, which was kind of went to non-production from the manufacturer. Then it was always a biggest headache for the hardware team or the designer to redesign the architecture accordingly. Always sometimes it will be having an alternate components like drop-in replacement, or otherwise sometimes it will be in kind of a small architectural change to make the same system to work without having an issues or without any hesitations. So AI will help in all of those phases, and in each every phase we can use the AI assistance. Further going ahead with respect to in different days or coming days, we will be designing or we will be seeing them by using a traditional way method, and we will be exploring how we can really use the AI in each and every phase also. And let us say for the mathematical calculations, you guys might already have idea with respect to this Ohm's law, this capacitive resistance axis, and with respect to all of these things, I'm skipping these lightly. Even if you want, the PPT will be remaining with you. You can have a look on this front. And tomorrow, with respect to these calculations, if you have any doubt, first 5 to 10 minutes we will be dedicated with giving a session for the doubts clarification, and we will be discussing further. For time being, for the mathematical calculation, I am skipping these two pairs, or I will just cover very high level. Like before designing the PCB, it is critical to perform various mathematical calculations and circuit design validations. This ensure that circuit functionally corrects and meets the power requirement and is safe and reliable. These calculations help in component selection, power management, circuit simulation, and unlimited, reducing errors and optimizing PCB layout. The major thing is like component selection and value calculations like resistors, capacitors and inductors. With respect to resistors, as it is simple, V is equal to IR. But when we are selecting a resistor in the real time, then another factor will also comes into a picture called wattage of a component. Like if you want to select an uh, resistor by if based on the ohms law, it comes up, let us say, of 10 ohms. But in the market, we should also think of what is the wattage we have to use that same of 10 ohms, because the same 10 ohms you can identify with 0.5 watt, with 1 watt, with 2 watts. But we should also think of the power constraint of the particular module also. So we should place the appropriate component, or otherwise it will lead to burnout of the component, and gradually it will degrade the component sometimes, and it will damage the PCB further going ahead. Sometime initially it might works very properly, but in real time site scenario issues, definitely it is going to break down. And so similarly, the capacitor resistors like 1 by 2 pi fc, based on the frequency where it operates and based on the voltage level where it operates, we will be selecting the capacitors. Inductors is xl is equal to 2 pi fl, based on the frequency where it operates and along with the current where it flows through it, we will be selecting the inductors based for our power supply requirements. And when we are considering every component or any component, always we should keep one thing in mind, like power. The power equation P is nothing but V into I, which helps for each and every component, or otherwise it will be going to lead in biggest issue. And as well as in similar way, when we are dealing with the PCB, it was always we should keep in your mind, trace is nothing but a wire. In similar way, how we see wires in our general analogy, the PCB traces are also comes with the same kind of uh, characteristics. Like if you can see, there are different kind of traces here. This is one width, this is one width. There is a difference of width in these traces based on the current requirement. Current requirement, the trace width will be varies. So this is the standard formula usually we will be follows. I is equal to K into A by dt, and the thickness and the width of the trace will also varies based on the component or based on the layer what we are using. Like it might be an copper, or it may be an aluminum, it might be a gold. Based on the thing what we are using, the things will be varies. Where K is a constant, material constant. For copper, it is ideally 0.024, and even in the copper also, based on the material composition, this value will be slightly varies. And further going ahead, we will be having a lot of benchmarks when we are dealing with the trade width and trade height. We will be discussing them in detail in coming days. Okay, but keep these analysis, these terms in the mind, so it will be easy for us when we are discussing them. Usually, before going for the PCB, we will call it as a POC, is nothing but proof of concept, where we will be having the testing and validation phase of this particular design to evaluate how truthful is this design. Because in lot of times we will simulate same kind of hardware with using different kind of simulation softwares like Proteus, how most of the colleges are going to be used. And there are a lot of hardware simulation softwares also. By using such kind of hardware simulation, we can simulate issues. So before going or jumping into the PCB, ideally we will be testing the same PCBs on the breadboard or pref board testings, like assembling the circuit using available modules and components. Use breadboards for quick and non-permanent prototype. Use pref board for semi-permanent setup with basic soldering. Breadboard is nothing but this, where on the top picture, and breadboard is like this module, where we will be soldering each and every component by using jumpers. Here we are functionally verifying each and every step or each and every module, like checking signal flows, logical operations, and input and output behavior of a particular circuitry or the module. And we will be measuring voltages, currents, and signals using multimeters or oscilloscopes based on the requirements. And ensure the main controller communication with peripheral module properly, and debug errors, optimize design, and document working prototypes. because once if you go into the development life cycle into the PCB, it will be both time consuming as well as cost consuming, because the manufacturing process as well as the fabrication process of a PCB, it is a costly affair. So before jumping into a PCB, we should be very well known with respect to the, or very well tested with respect to the module or the schematic or the circuitry with respect to each and every module in detail. And the major outcomes by using these breadboards or breadboard testings is like confirms practical feasibility of the design, provides low cost method to detect design flaws very early in the initial phase, because when we are testing, we will usually figure out, okay, this is going to fail more of the times, or by using this method we can, if we provide few debug options, this will be easy to identify if there is any default. Such kind of things will also be noted in the early phases before going, doing and jumping something. Okay, and lays groundwork for the final PCB design by using these things. And when and why to transition to PCB design? Coming to that, after successful breadboard and pressboard testings, complete testing of circuits functionality and performance, ensure all modules working as intended in real conditions, avoid premature PCB designs to prevent costly redesigns and delays. Debugging is easier on the breadboards than the soldering PCBs. It was always to be noted in the mind. And when signal integrity, power efficiency, and EMI reductions are also very needed. That is the reason, the main reason we will be jumping into the PCBs. For that, PCB offers superior electrical performance over loose wires for very sure, because it was having a proper insulations and proper uh, coatings with respect to reduce the EMI reflections and everything. We will be discussing them also. Enable precise power distribution, reduces voltage drops, improve signal integrity using proper routing techniques by for the differential pairs or for the longer pairs, as well as for the parallel buses for a lot of this kind of stuff, and reduces EMI with optimized layout and grounding techniques when we are designing the PCBs. Okay, for product miniaturization and long-term stability, PCBs allow compact designs for portable consumer ready use devices. Use of multi-layer PCBs, we can go for 2 layer, 4 layer, etc. There is no such kind of practical limitations to extend the number of layers, but lot of engineers or lot of things we will usually limit until the 16 layers. If we go beyond 16 layers, it will be always very difficult to debug the PCB if it goes into the very fault mode, to save the space constraints. Okay, and from soldering connections, avoid the unreliability of jumpers and loose wires, and supports durability, portability, and long-term usage also. And usually the designing circuit schematic and PCB design. Ideally, we will call the schematic is nothing but in circuit layout. To do the same circuit layout or the schematic design, there are a lot of other tools like using KiCad, RTM design, Eagle, or ArcCAD. There are even many more design tools also. The main reason is to connect the microcontrollers, sensors, actuators, and power sources. Select the necessary passive and active components. Ensure signal integrity, noise reduction, and minimal power use. Circuit diagram or schematics, the same analogy, but in industry we will call schematic design. That is nothing but a circuit diagram, like how in our labs with respect to universities or in the colleges we will call it as a circuit diagram. The same thing we will call it as a schematic design in the PCB layout. In the PCB layout designs, convert the schematic to the actual PCB layout positions and defines the traces, ground planes, vias, components placement, and optimize PCB size and shape as we require, and performs design rule checks that also pre-defined by us. Based on the product requirement, we will be varying those design rules, and implementing the thermal managements like heat sinks, thermal vias, thermal pads, and many more. Basically, why to transition into the PCB is like to increase the scalability, to cost efficient the module, to make it so professionalism, and to avoid loose wires on the boards and compactness, to increase the reliability, and to go for the mass productions, and to manage the thermal things on the PCB. These are the main core requirements we will be jumping into PCB designs. And AI will assist us with respect to using the schematic generation. Like if we have a very clear cut idea what to do and how to do, AI will help us. Right now, the AI is already ahead with respect to a lot of models to generate the circuit design however we wanted to. Like AI generates circuit blocks for common functional requirements, suggests appropriate component footprints and land patterns. We will be seeing what is meant by footprint, what is meant by landmarks in the further days. Don't no worry on those points. And designs protection circuits for over voltage and over current. Recommended decoupling capacitor placement near power pins with respect to the placement and when we are dealing with the designs, and creates preliminary bill of material with part numbers. I will be explaining what is meant by bill of material and what is meant by part number. No worry on that front. Okay. Part number ideally means, just to give you an idea, it is in code to each and every component. Usually the part number will be unique for each and every component in the world. So if you name a resistor with a particular part number, it will be unique for each and everything. If you Google it out a part number in the Google search, it will be unique. Just to keep that in the mind. And speed and productivity benefits. Sorry? Speed and productivity benefits, like enables rapid design, iteration and faster prototype cycles, allows parallel exploration of multiple design alternatives, automate repetitive tasks and reduce manual efforts, minimize cost design rework through early issue detection, generates technical documentation quickly and consistently without having any issue. By using AI, we can do these kind of works very fastly. The main thing is like allows parallel exploration of multiple designs alternatives. In an olden days, we use it to work like 2 or 3 teams. If it requires to work on parallel, at the same time will work on different architectures one after another. But by using an AI, we are working rapidly on multiple designs with a fewer team members, or with the same team members we can work very fastly also. And the quality and reliability benefits are also very highly increased by using this artificial intelligence technologies, by like identifies potential defects early in the design phase only, and ensures consistency across design, decision and standards, reduce common human errors in the calculations and routings, optimizes component placement and trace route efficiently, improves compliance with design rules and manufacturing specifications also. And even though it is having very high use cases, there are a lot of limitations with respect to by using an artificial intelligence. Like AI lacks understanding of broader system context and its goals, may miss rare edges cases and not present in the trained data. Usually we know AIs will run on the models, so it will be, we cannot barely depend upon any AI. That is what I have said in the very beginning also. And performance depends heavily on the quality of training of data sheets or data sets, sorry, cannot replicate human intent and experience based on the insights. Like how we discussed, like the field scenario will be different from case to case, so AI cannot predict or AI cannot assume those kind of field side scenarios and work accordingly, and requires continuous human oversight and validation whenever there is an input from a AI. That should keep in our mind. And thank you with respect to the session, and we were ready to have any doubts related to the session or something. We will be first seeing the chat box and we will be proceeding with the vocal doubts if there is any. Like notes or PPT will be shared. I think PPT will be shared along with the recorded video also. No need to note. If you have any points to be noted, it's your wish, sir. You can proceed. Sir, please. Okay. Please share, please share. Okay. There is no such any doubts as raised in the chat session. If anyone is having any queries, please, the room is open to discuss. If you guys are not having any doubts, you are feel free to leave the room also, no problem. And thank you for the attending the session. We will see you tomorrow.
Yeah, attendance is auto tracked. You can leave. Yeah, so, Sai Shankar.
Yes.
Hold on.
How to identify components through AI. Yes, sir. Yes, we are discussing today with respect to what are the major roles of AI. When we are in the phase of seeing a component selection, I will explain what is the traditional way, and we will also explain by using AI how we are doing that. When we are doing that, I will definitely address this question and we can cover that. Still, if you have any doubt, we will be discussing them.
For recording sessions, please check your mails. Already we have shared the playlist.
How to find out best components using AI? Sir, definitely when with respect to the component selection session, we will be addressing all of these questions, sir. Okay, sir. How to clarify the doubts in recording classes? As I said, sir, every day, as today is an initial day, we have initially started the class, but ideally this is the reason, this is an 1 hour session, but ideally from tomorrow after from 7:30 to around 7:40 or 7:45 based on the time permits, we will be discussing regarding the doubts. The doubt session will be having in the initial phase as well as in the latter phase for the 5 to 10 minutes based on the class what is going to be happen. Then we can discuss, sir. Still, if you are seeing all the videos in the online mode, just drop the doubts in the YouTube comment section. The team will reach out to you or the team will give you comments for that section.
PPT is also shared through mail only. You please check your mail thoroughly.
Sometimes the PPTs or the videos might come little bit delay. Don't get worry. It 2 to 3 days videos and PPTs are by the end of 15 days, all of them will be reached to you. No need to worry on that. Okay, guys, then thank you once again. See you tomorrow.